In thermophysics, there are four commonly used thermodynamic potentials. Gibbs free energy G is one of them, and it is very useful when dealing with equilibrium, compatibility or miscibility, phase transformation, etc. It is defined as G equals to U times PV minus Ts, which is equivalent to enthalpy H minus Ts. From the fundamental relation, we know the differential form of internal energy U is given by du equals to Tds minus Pdv. Since dg equals to du times dpv minus dts, by applying transformation, we have dg equals to vdp minus x dt, where we can see that p and t are the natural variables of g. P and T are easily manipulated experimentally in the thermodynamic system. This is why Gibbs free energy is very useful for a constant temperature and pressure system, thanks to the fact that it is minimized at equilibrium in such a system. So we can determine if equilibrium has been reached by finding out if the entropy of the system is maximized. In another word, when we consider the slope or curvature in the diagram in which the first order derivative equals to 0 and the second order derivative should be negative. Or in a system at fixed pressure and temperature, we look at if the Gibbs free energy is minimized, in which the first order derivative is 0 and the second order derivative is positive. If the overall Gibbs free energy change, dg equals to dh minus tds, is less than 0, we say the process is thermodynamically favored, or spontaneous. One example of utilizing the Gibbs free energy consideration is to determine the miscibility of polymer blends by predicting the polymer's phase separation. Polymer blends are physical, but not chemical, mixtures of two or more structurally different polymers or copolymers, which are mixed when they're in the molten state. You may be wondering why. Well, by doing so, production costs can be reduced and tailored mechanical properties can be obtained, which means the blending can give rise to properties that are not deliverable by its constituent polymers. Polymer blends can be miscible or immiscible. To determine the miscibility, we look at the Gibbs free energy due to mixing, where Hm and Sm are enthalpy and entropy of mixing at a given temperature. The polymers in the blend are only considered miscible if two conditions are met. First, delta Gm must be smaller than 0, and secondly, the second order partial derivative of G with respect to phi at a fixed temperature and pressure is greater than 0, where phi refers to the volume fraction of a component. This suggests favorable mixing of the polymers. Another interesting phenomenon is phase transition, which occurs when a change results in decrease of Gibbs energy of the system. There are first order and second order phase transitions. First order phase transition is something we are all familiar with. For example, melting of ice. This type of phase transition involves latent heat and is characterized by distinct macroscopic property changes like density or entropy, etc., at the phase boundaries. The first order derivatives of G are discontinuous. This is the reason why water expands when turning into ice, since during the phase transition, there is abrupt change in volume which happens to be equal to partial G partial U with temperature fixed. Another example of first order phase transition is melting of crystalline polymers, which occurs at crystalline melting temperature Tm. It involves latent heat, leading to breaking of ordered lattice structure. Thus, there will be distinct changes in atomic packing factor, volume, entropy, and other macroscopic properties. while second-order phase transition occurs without latent heat. This time, the first-order derivatives of G are continuous, and that's why second-order phase transitions are gradual and continuous, while second-order derivatives of G are discontinuous. An example is glass transition of an amorphous polymer from a rubbery state to a glassy brittle state, which occurs at the glass transition temperature Tg. By the way, it's difficult for all polymers chains to become aligned, so there is rarely 100% crystalline polymer. Practically, there are only amorphous and semi-crystalline polymer, which consists of both crystalline and amorphous domains, with intermediate properties between that expected from a completely crystalline and completely amorphous polymer. And that's a brief introduction to how Gibbs energy tells us if a reaction will happen on its own. Hope it helps.